Hi students, welcome to Renju at Physics. Today is a new session. Okay, today we are going to start with the electrostatics of conductor. We are going to discuss electrostatics of conductor. In that we are going to discuss electrostatic properties of conductor. What are the electrostatic behavior shown by the conductor? Okay, when we are placing a conductor in electric field, what are the properties are shown by the conductor? Okay, that we are going to discuss today. So the first property shown by the conductor when we are keeping inside the external electric field is the net electric field is zero in the interior of a conductor. The net electric field is zero in the interior of a conductor. The effective electric field in the conductor is zero when we are keeping the conductor in an external electric field. So we can discuss how the electric field will be zero inside a conductor. Okay, so here there are two plates. This is a positive plate and this is a negative plate. Okay, so between there will be electric field. So this is external electric field. E0 is external electric field. Okay. We are keeping a conductor in between the plate. We are keeping a conductor between the plate. So this is the direction of electric field. This is the direction of external electric field. So we consider metal plate. One is positive and another one is negative. So external electric field is acting from positive to negative direction. So we consider a conductor. Now our conductor consider conductor equal is actually it is neutral. Positive charge and negative charge equal. Okay. So when we are keeping a conductor in an external electric field, okay, all the positive charge inside the conductor, all positive charge move negative plate in the side move the same way all the negative charges move towards the negative plates, positive plate side. All the negative charge move to the positive side plate. So electric field is set up inside the conductor. The electric field is induced inside the conductor. Okay. Now a conductor electric field all positive charge negative plate in okay, all negative charge and positive plate in separate. Now, this conductor is electric field induced. But the separation will be stop. After separation stop, okay, the induced electric field is equal to E induced is equal to the external applied electric field. Okay, the induced electric field, okay, is equal to the applied or external electric field. Then the separation between the positive charge will stop. Okay, that is in the conductor induced electric field external electric field equal in the conductor positive charge and negative charge in separation continues. So the net charge inside the conductor, so the net charge so the net electric field, so the net electric field can be represented by E net is equal to, and it is found that here external electric field is in this direction, induced electric field in this direction. That means induced electric field is opposite direction of the external electric field. So the net electric field it will be E0 minus E induced. E net is equal to E0 minus E induced. But here E induced and E0 are same. So what will be the net electric field? E net is equal to 0. So we can conclude the net electric field inside a conductor when we are keeping in an external electric field will be 0. അപ്പം ഇവിടെ നെറ്റ് ഇലക്ട്രിക് ഫീൽഡ് നമുക്ക് കണ്ടുപിടിക്കാം. E0 മൈനസ് E ഇൻഡ്യൂസ്. നമുക്കറിയാം E induced and E0 are equal. Okay, so E net is equal to 0. So എന്ത് കൺക്ലൂഡ് ചെയ്യാം? ഒരു കണ്ടക്ടറിന്റെ ഉള്ളിൽ നെറ്റ് ഇലക്ട്രിക് ഫീൽഡ് എപ്പോഴും എന്തായിരിക്കും? 0 ആയിരിക്കും. So that is the first property of a electrostatic behavior of a conductor. The second property, just outside the surface of a charged conductor, electric field is normal to the surface. That is the second property. Okay, so we know that electric field have two components. One is E cos theta and E sin theta, parallel and perpendicular component. Okay, if the normal component is not there, ഇപ്പോൾ നമ്മൾ ഇലക്ട്രിക് ഫീൽഡ് നോർമൽ കമ്പോണന്റ് അവിടെ ഇല്ല എങ്കിൽ, എന്ത് കമ്പോണന്റ് ഉണ്ടാവും അവിടെ? There will be a tangential component. Normal component is E sin theta, tangential component is E cos theta. Okay, if electric field is not normal, surely there will be a tangential component. If there is tangential component, surely the charge will flow through the surface. അവിടെ ടാൻജൻഷ്യൽ കമ്പോണന്റ് ഉണ്ടെങ്കിൽ ആ സർഫസിന് കൂടെ എന്തുണ്ടാവും? ചാർജിന്റെ ഫ്ലോ ഉണ്ടാവും. ബട്ട് ഹിയർ ഇത് സ്റ്റാറ്റിക് സിറ്റുവേഷൻ. ഇവിടെ നമ്മൾ കൺസിഡർ ചെയ്യുന്നത് എന്താണ്? സ്റ്റാറ്റിക് സിറ്റുവേഷൻ ആണ്. സോ charge is not flowing. That means the tangential component is 0. That is E cos theta is 0. E cos theta is the tangential component. E cos theta is 0. Here theta is the angle which electric field intensity make with tangent to the surface. Here theta is the angle which electric field intensity make with tangent to the surface. Clear? If there is no normal component ഇല്ലെങ്കിൽ surely അവിടെ എന്തുണ്ടാവണം? ടാൻജൻഷ്യൽ കമ്പോണന്റ് ഉണ്ടാവണം. ഈ ടാൻജൻഷ്യൽ കമ്പോണന്റ് ഓഫ് ഇലക്ട്രിക് ഫീൽഡ് ആണ് എന്ത് പ്രൊഡ്യൂസ് ചെയ്യുന്നത്? The flow of charges പ്രൊഡ്യൂസ് ചെയ്യുന്നത്. പക്ഷെ ഇവിടെ എന്തില്ല? ഇത് എ സ്റ്റാറ്റിക് സിറ്റുവേഷൻ ആണ്. സ്റ്റാറ്റിക് സിറ്റുവേഷൻ ഓഫ് കണ്ടക്ടർ ആണ് നമ്മൾ കൺസിഡർ ചെയ്യുന്നത്. അപ്പൊ E cos theta എന്ന് പറഞ്ഞ കമ്പോണന്റ് എന്തായിരിക്കും? 0 ആയിരിക്കും. So E cos theta is equal to 0. In this equation, E not equal to 0. So which one will be 0? Cos theta is equal to 0. Cos theta is equal to 0 means surely what is theta? Theta is equal to 90 degree. So we prove that just outside the surface of a charged conductor, electric field is normal to the surface. Okay, so here I told what is theta. Theta is the angle which electric field intensity make with tangent to the surface. Okay, here theta is 90 degree. That means the outside the charged conductor electric field is normal to the surface. Is it clear? Now we are going to discuss the third property. So this is the third property. The net charge in the interior of a conductor is 0. The net charge in the interior of a conductor is 0. Otherwise, no excess charge reside inside a conductor. Okay, that we are going to discuss now. Okay, so we consider a conductor. So this is a conductor. Okay, the charge is there. So all electric field is acting normal to the surface. And here positive charge is distributed. Okay, so we have to prove the net charge in the interior of conductor is 0. So here this is a static situation. Okay, we consider a conductor. Okay, so here we consider a Gaussian surface. Just below the boundary. So we consider a Gaussian surface just below the boundary. So this dotted line represents the Gaussian surface. So what we need to prove? We need to prove net charge in the interior of conductor is 0. So we consider a conductor. The charge is distributed over the surface. Electric field is normal to the surface. Okay. Now we consider a Gaussian surface just below the surface of a conductor. Now Gaussian surface consider a conductor just the Gaussian surface consider and take flux through the Gaussian surface. Take the flux to the Gaussian surface. So the flux phi is equal to E dot ds, that is equal to Q by epsilon 0. Okay, Q by epsilon 0. So now we are going to find the flux to the Gaussian surface. The flux is given by phi is equal to E dot ds, that is equal to Q by epsilon 0. But inside the conductor, electric field is 0. Inside the conductor, electric field is 0. So based on this equation, we can write Q by epsilon 0 is equal to 0. So we can write Q is equal to 0. That means inside the conductor there is no excess charge. All the charge are present on the surface. Is it clear? So here we found that the total charge inside a conductor is 0. From this we can conclude that the entire excess charge must be reside on the surface of a conductor. Okay, that is the third property of conductor. The third property is the net charge in the interior of conductor is 0. Now, we conductor consider chedu, while charge distributed under electric field normal. Okay. Now just a Gaussian surface consider just below the surface of a conductor. That flux. So now inside a conductor electric field is 0. Q by epsilon 0 flux is 0. Q by epsilon 0 0. Epsilon 0 equals 0 is a constant value. So which will be 0? Charge will be 0. So from this we conclude that all the excess charge are residing on the surface of a conductor. Okay, all the excess charge must be reside at the surface of the conductor. That is the third property. And next one is now the fourth property. The potential is constant within and on the surface of a conductor. That is, ഒരു കണ്ടക്ടറിന്റെ ഉള്ളിലും സർഫസിലും ഉണ്ടാകുന്ന പൊട്ടൻഷ്യൽ എന്താണ്? കോൺസ്റ്റന്റ് ആണ്. The fourth property പറഞ്ഞിട്ടുള്ളത്. So we need to prove how the potential is constant inside and on the surface. Okay, we know that electric field at a point. Is the negative gradient, negative of the potential gradient. We know that the potential at a point is negative of the potential gradient, that is dV by dr. Okay, but we know that inside the conductor electric field is 0. We know that inside the conductor electric field is 0. So what will happen to this equation? 0 is equal to minus dV by dr. 0 is equal to minus dV by dr, that is dV is equal to 0. dV is equal to 0. Okay, change of a value is 0 mean that should be a constant. So we can say V is constant. We can say is constant. So dV is equal to 0. So change of potential is 0 mean the potential is constant inside and also on the surface of a conductor. That is the fourth property. Clear? This is the fifth property. The electric field at the surface of a charged conductor. Is equal to sigma by epsilon 0. That is the fifth property of conductor. So we need to prove electric field on the surface of a conductor is sigma by epsilon 0. Here we consider a conductor of irregular shape. So we consider a conductor of irregular shape. Okay, we consider a conductor of irregular shape. So this is a conductor. Okay, here we consider sigma is greater than 0, charge of the surface is positive. Okay, so we know that inside the conductor electric field is 0 and V is constant. Okay, so we need to prove this one. So we consider conductor consider sigma greater than 0 on a charge positive consider inside the conductor electric field and 0 on a potentially constant. So we consider a point. We consider a point just near the surface of a conductor. The point is very close to the surface of a conductor. Okay, so we need to find out the electric field at this point. The point is very close to the surface. So we need to find out electric field at that point. Okay, for finding that we consider an imaginary Gaussian surface. We consider an imaginary Gaussian surface. We consider a Gaussian surface in the form of a cylinder. So one part of cylinder is partially inside the conductor, one is outside the conductor. So I will draw a cylinder here. This is a cylinder enclosing the point. So one part will be inside and one part will be outside. So at this point, we know that on the surface electric field is normal to the surface, and we consider ds is the area of cross section. So the area vector is also in the same direction. Area vector is also in the same direction. First, we are going to find out the flux through the Gaussian surface. First, we are going to find out the flux through the Gaussian surface. So the flux through the Gaussian surface is given by flux through the Gaussian surface. First is phi is equal to E dot ds. But here E and ds are in the same direction. We know that E ds cos theta, but theta is 0, but E and ds are same direction. So phi is equal to E ds. So that is the flux through the Gaussian surface. Okay, next, apply Gauss's law. Apply Gauss's law. We know that Gauss's law is given by the flux phi is equal to Q by epsilon 0. The flux is Q by epsilon 0. Here I told sigma is the charge density. Okay, so the charge enclosed by the Gaussian surface, can be written as Q is equal to sigma into ds. The charge enclosed by the Gaussian surface, it will be Q is equal to sigma ds. We know that sigma is equal to charge by area. Here area is ds. So the charge enclosed by the Gaussian surface, it is Q is equal to sigma ds. So equation 2 changes to equation 2 can be written as the flux phi is equal to sigma ds by epsilon 0. That is equation number 3. That is equation number 3. So from equation number 1 and 3, both are giving the flux. Equation number 1 and 3, both are giving the flux. So we can write E ds is equal to, that is equation number 1, that is equal to sigma ds by epsilon 0. So here ds we can cancel, then we can write E is equal to sigma by epsilon 0. E is equal to sigma by epsilon 0. So in vector we can write E vector is equal to sigma by epsilon 0 in cap. This is normal to the surface. So the property, which property it is? It is the fifth property of electric. So on the surface of electric field is given by E is equal to sigma by epsilon 0. Okay, the sixth property. So electric field is 0. Electric field is 0 in the cavity of hollow charge conductor or electrostatic shielding. Okay, or a conductor or a cavity consider electric field 0. So we consider a conductor, it's a cavity. Okay, so we consider a conductor. This is a conductor having a cavity. So this is a cavity. Okay, so we consider a charged conductor with the cavity. Okay, inside the cavity there is no charge. Inside the cavity there is no charge, but on the surface of a conductor there will be charges distributed. So direction of electric field is always normal to the surface. This is the direction of electric field. Okay, so what we need to prove? Electric field is zero in the cavity of hollow charged conductor. So we consider a charged conductor with a cavity. The cavity does not have any charge. Okay, on the surface charge is distributed. So for proving that, we consider, and we know one thing: electric field inside the conductor E is equal to 0 and V is constant. V is constant. So in order to prove, we consider a Gaussian surface near the cavity. We consider a Gaussian surface very near to the cavity. So we consider a Gaussian surface very near to the cavity and take the flux through the Gaussian surface. Take the flux through the Gaussian surface. The flux phi is equal to E dot ds. And we know that inside the conductor, that Gaussian surface actually is inside the conductor. So electric field is 0. So flux will be 0. Flux will be 0 means Q by epsilon 0 is 0. So Q is equal to 0. The charge is 0. That means the charge in the cavity will be 0. That means the Gaussian surface does not enclose any charge. Gaussian surface does not enclose any charge. That means inside the cavity there is no electric field. If the charge is present, then no electric field will be there. So here Q is equal to 0. So electric field inside the cavity will be 0. Is it clear? So the entire charge lies only on the surface of a conductor. Okay. So from this we can conclude that the cavity inside the conductor, remain shielded from the outside electric field or electric influence. From this we conclude that the cavity inside a conductor remain shielded from outside electric forces or outside electric influence. This is known as electrostatic shielding. Or otherwise, the phenomena of making a region free from any electric field. Is called electrostatic shielding. Okay, electrostatic shielding means the phenomena of making a region free from any electric field is called the electrostatic shielding. And the electrostatic shielding is based on the fact that electric field vanishes inside the cavity of a hollow conductor. That is the principle of electrostatic shielding. So the electrostatic shielding is based on the fact that electric field vanishes inside the cavity of a hollow conductor. Okay. So electrostatic shielding, lot of uses are there. Okay. Today we discuss the electrostatic properties of the conductor. Okay, the first property we discussed, electric field interior of a conductor is 0, and second one is the electric field on the surface is always normal to the normal direction, and third one, okay, all the excess charge is on the surface of a conductor, and third next one we discuss inside a conductor potential is constant. And next property we discuss, on the surface of a conductor electric field intensity is given by E is equal to sigma by epsilon 0, and last property, that is electrostatic shielding.